In this video, we're going to have a look at circular motion and the theory behind it. It's exclusive to the Extension 2 course, so if this is your first time seeing it or experiencing circular motion, then it may seem a little bit daunting or confusing at first, but not to worry, just try to follow along and we'll do the best that we can. So, we're going to start by considering a particle which starts at the x-axis and it moves around a circle of radius r, which is centered at the origin. And after a certain amount of time, say t units of time, it reaches the point P. Now, when it reaches the point P, it will create or form an angle of theta with the x-axis. Alright, now, this position P, it can be defined in two ways. It could be defined, let me just get my pen, it could be defined as either x comma y, so simply just the x and y coordinates, and this is called the rectangular or the Cartesian coordinates of P, or it could be defined in terms of r comma theta, where r is the radius and theta is this angle here. Now, if we define in terms of r comma theta, which is called the polar representation or polar coordinates, if we define in terms of theta, then theta is the angular displacement. Okay, so it's just the amount that the particle has moved from its starting position, which is what a displacement is, but we're just measuring it in terms of theta. Okay, so if I have this, well, let's draw something on our diagram. If we were defining it in terms of x and y, this would be the y coordinate, and this would be our x coordinate. So, our x coordinate, if I was to relate that to the polar coordinate, well, this is going to be adjacent over hypotenuse. So I'm going to have r cos theta. And similarly, y is going to be r sine theta, because this time it's going to be, well, this would also be y. So this would be opposite over hypotenuse. So this is just basic trig. Okay, and let's just remember these because we're going to need to use them later. Okay, and what else can we say? Well, if my particle is moving along a circle, then the distance that it travels from here to the point P, if I call that distance s, I can work out the length of that distance, and that is given by the length of the arc of a circle, which is just s equal to r times theta. And that's if theta is in radians, don't forget that. Theta should be in radians. So here I've related my linear displacement, which is the distance that I've traveled away from my starting point, s, to my angular displacement, which is theta. Alright, now let's relate the linear and angular velocities to each other. So first, let's define what our angular velocity is. So, define angular velocity as the rate of change of the angular displacement with respect to time. And we will give it its own little letter, omega. That's going to be equal to d theta on dt, the rate of change of the displacement, of the angular displacement, with respect to time. And sometimes we denote that by phi dot. Okay, now let's have a look at our velocity. Our velocity vector, now let's just draw this to the side so we have it more clearly. Our velocity vector, v, can be decomposed into two parts, into a vertical component, which is our y dot, our y component of the velocity, and also into our horizontal component, x dot, which is our horizontal component of the velocity in the x direction. Okay, so I have x dot. Now what is x dot? It's the derivative of x with respect to time, the x displacement with respect to time. And what did we say x was? We said that that was r cos theta. So I'm differentiating r cos theta with respect to time. Okay, I'm moving in a circle, so my radius is obviously going to be constant. So that's fine. Now what about differentiating cos theta with respect to time? Well, I'm going to use the chain rule, or you might know it as implicit differentiation. I'm going to differentiate it with respect to cos, and that is, with respect to theta, and that will give me sine theta, but I have a negative, so it's negative sine theta, and then I have to multiply that by d theta on dt. And now let me just write this as minus r sine theta times theta dot. We're going to use that notation. And similarly, I can do the same for y dot, which is going to be dy on dt, which will be differentiating r sine theta with respect to t. And that's going to give me r cos theta d theta on dt. And again, I'll write it using that dot notation times by theta dot. Okay, so now that we have these expressions for x dot and y dot, we're going to go to our triangle that we have up here, and we can see that this is a right-angled triangle, and so I can apply Pythagoras' theorem to find the magnitude of v. So to do that, it's very simple. The magnitude of v is going to be the square root of x dot squared plus y dot squared. And then I substitute in those values that I just worked out. For x dot, it was minus r sine theta times theta dot, all squared. And for y, it was r cos theta times theta dot, all squared. And I take the square root of that. Now, when I take the square of this, the negative will go, and I'll have r squared sine squared theta dot squared. And here I'll have r squared cos squared theta dot squared. So I can take out a factor of r squared theta dot squared from each term, and then when I take that outside of this square root, it'll be left with r times theta dot. And inside I'll have square root of sine squared theta plus cos squared theta. Now, we know that this is simply just 1 for all values of theta, and then the square root of 1 is 1, so I'm left with r times theta dot, but I'm going to call theta dot omega, which was the angular velocity. So here I've related the linear velocity, the magnitude of the linear velocity, to the angular velocity. Now, we know that this is a velocity, so it doesn't just have a magnitude, but also a direction. So for the direction of v, what do we have? Well, again, going back to our triangle, this is going to be the tan inverse of y dot divided by x dot. So the angle is the tan inverse of y dot on x dot. Now if I substitute these values back in, I'll have tan inverse of y dot, which is r cos theta times theta dot, divided by negative r sine theta times theta dot. Okay, theta dots will cancel, r's will cancel, and I'm left with tan inverse of minus cosine sine, which is cotangent or cot theta. And what is negative cot theta? Well, negative cot theta is tan of theta plus pi on 2. Hopefully you can see how that is. If not, you need to think about that. Okay, and then tan inverse and tan are inverse functions, so they'll cancel each other out, and I'm left with theta plus pi on 2. And so this is my direction for v, and it's related to the direction of omega, which was theta. So it's just adding on 90 degrees or pi on 2 radians. Alright, so now to relate the linear and angular accelerations. So again, I will need to define what I mean by an angular acceleration. So an angular acceleration, I will define it as alpha, which is equal to the second derivative of displacement with respect to time. So d2 theta on dt squared, the second derivative of angular displacement, I should say, which is also equal to the first derivative of the angular velocity with respect to time. And then I have two notations, two alternative notations, theta double dot or omega dot. Now we rarely see omega dot, but nevertheless it is sometimes used, and so these are our notations for it. Alright, so our x dot, now firstly let's have a look at our diagram. Now this is the diagram that we would have for our accelerations. The acceleration in the y direction is upwards, and the acceleration in the x direction is actually to the right, which seems counterintuitive, but once we do our next step, you'll see why this is actually drawn in this manner. So, x double dot, well that's the derivative of x dot with respect to time, and what was x dot? That was negative r, so d dt of negative r sine theta d theta on dt. So now I'm going to use product rule. Differentiating the first term, sine theta, with respect to t, I'll get minus r. Now differentiating sine with respect to t is the same as differentiating with respect to theta and then multiplying by d theta dt. So differentiating the first one will be cos theta times d theta on dt. And then I'm left over with this, so I multiply by that again, d theta on dt. And now I leave the first function and differentiate the second function. So to do that, it's going to be minus r sine theta. Differentiating this with respect to t would give me the second derivative, d2 theta on dt squared. And let me write this using the theta dot notation, or theta double dot notation. And at the same time, I'm going to factor out a negative r. So minus r. Here I'll have cos theta times by what? Well, this is theta dot, and this is theta dot, so I'll have theta dot squared. And here I'll have plus sine theta. This is theta double dot, multiplied by theta double dot. Great, that's my x double dot. And what about my y double dot? Well, that's equal to the derivative of y dot with respect to time. So no negative, it's positive cos theta d theta on dt. And that's equal to, differentiating the first with respect to time will be minus r sine theta times by d theta dt, or theta dot. And what's this? This is also theta dot, so there's a squared. And now I leave the first and multiply the second, and derive the second. So that's r cos theta, and again I get d2 theta on dt squared, which I should have written as theta double dot, but never mind. Now I'll just factor out an r, and I'll have minus sine theta times theta dot squared plus cos theta times theta double dot. And so these are my x and y accelerations. So acceleration in the x and y direction. Okay, now let's have a look at our diagram. We're moving in a circle, so it would make sense that we would consider directions which are related to a circle. So we will choose now to have our directions of tangential and normal direction. So let's move this out of the way, and let's say something about this. Alright, we're going to choose, we choose to have tangential and normal components for acceleration. And that makes sense because we're traveling in a circle, so these are things that are related to a circle. Alright, let the tangential be in the same direction. Let the tangential be in the same direction as the velocity. So in other words, now velocity, I mean linear velocity. In other words, it's going to be in this direction, from here outwards, upwards rather. And let the normal component, the normal, be in the direction outwards from the center. Outwards from the center. So it's going out this way. Let's move it out this way. Okay, so now we need to decompose the y acceleration and the x acceleration into components of tangential and normal directions. So to do that, here I'm going to have a normal component like this, and I'll have a normal direction. Now the normal one should be parallel to the radius, because this is the direction of normal component. So if I just move that vector over, it'll be like this, and that is parallel to this line, the radius. So this here is y double dot in the normal direction, in the normal component, and this is y double dot in the tangential direction, or the tangential component. And I'm going to do a similar thing for x double dot. Now, the tangential component will be this way. Now, this is not very well drawn, but you get the idea. And this is x double dot in the normal direction, and this one is x double dot in the tangential direction. Okay, so now let's go ahead and work out what our overall acceleration in the tangential direction is. So, the acceleration in the tangential direction is going to be equal to, well, we defined it as being in the same direction as the velocity. So it's going to be yt, y double dot t, which is already in the same direction, so that'll stay positive, plus x double dot t, but x double dot t is in the opposite direction, so it's going to be minus x double dot t. Now, what are y double dot t and x double dot t? What are these? What are these equal to? Well, let's have a look. If I have this angle theta, now let's draw it in so we have a complete diagram. If I have this angle theta here, then that means that if I extended that out, this angle would also be theta, which means that this angle, since this is a right angle, is pi on 2 in here, and this is a right angle, so by angle sum of a triangle, this is theta. And I can make a similar argument and say, well, by right angles, this angle in here is pi on 2. If this angle is pi on 2, then this angle here is, is pi on 2 minus theta, and so that means this angle in here is theta. So I will get the following. I will get that x double dot in the normal direction is equal to x double dot cos theta. This is just basic trig now, using our triangles, and noting that these are right-angled triangles. So let me just indicate that as well. This is right-angled, and that's right-angled there. Okay, so x double dot cos theta, x double dot in the tangential direction is going to be x double dot sine theta, and for y double dot in the normal direction is this one, so this is going to be y double dot sine theta, because it's opposite over hypotenuse, and the tangential will be y double dot cos theta. Okay, now I'm going to use these when I'm working out my acceleration in the tangential direction. So this is equal to what? Y double dot cos theta minus x double dot sine theta. X double dot sine theta. And now I substitute in my y double dot and x double dot, which I have worked out here, these ones. So subbing these in, it will get a little bit messy. Now I'm subbing in for y double dot. So that is r minus sine theta times theta dot squared plus cos theta times theta double dot times by cos theta, and minus, what's x double dot? Well, x double dot is minus r, so this minus and another minus will give me a plus, r cos theta times theta dot squared plus sine theta times theta double dot, and then that is times by sine theta. And if we were to expand this out, we'd have here a negative of r sine cos theta dot squared, and here we'd have a positive of r sine cos theta dot squared. So they're the same, but just with a different sign, and so this term, when we expand it out, will cancel with this term here. And so I'll be left with r times minus cos squared theta times theta double dot, and sorry, this will be a plus, that's a plus, and here I have r times sine squared theta, theta double dot. So if I factor out an r theta double dot, I'll be left with cos squared plus sine squared, which is just equal to 1. And so here I have that the tangential acceleration is equal to r times theta double dot. Okay, now for the normal direction. Well, in our diagram, we can see that both y in the normal direction, y double dot in the normal direction, and x double dot in the normal direction are both in the positive direction as we have defined it, and so it will just be the sum of the two, x double dot n. So that's going to be y double dot sine theta plus x double dot cos theta. Now, substituting our values in again for y double dot, that's r times minus sine times theta, not phi, theta dot squared plus cos theta times theta double dot. And now instead of cos theta, it will be timesing by sine theta plus x double dot. Now, x double dot was minus r, so this shouldn't be a plus, this should be a minus r cos theta times theta dot squared plus sine theta times theta double dot. And then I multiply that by cos. Again, I'm going to get cancellations, which will come from where? They'll come from the cos and the sine terms. So that those two will cancel. And I'm left with what? I'm left with, let's see, minus r sine squared theta, theta dot squared, let's put these in brackets, minus r cos squared theta, theta dot squared. I factor out a minus r theta dot squared, and then I'm left with sine squared plus cos squared, which is itself 1. And so I have in the normal direction minus r theta dot squared. Great. Now, we have defined by our own choice to let the normal be in the direction outwards from the center. So, r is obviously positive. Well, the angle, whatever it is, if I square it, it's going to be positive. So this term without the minus is positive, but with the minus is negative. So our direction, although it's pointing outwards, is really inwards, because when we point outwards, it's always negative. So in other words, we flip the direction, and this is telling us that the direction of the normal acceleration is always inwards. towards the center of the circle. Towards, that's one word, towards the center. And this has a specific name. It's called the centripetal force or centripetal acceleration. So this is called the centripetal acceleration. And it always goes towards the center. In other words, it's center seeking. Now, one thing that's important to know about centripetal acceleration is that there is no physical force called centripetal acceleration. Centripetal acceleration is a resultant force. So what do I mean by that? Well, let's consider I have a ball on the end of a string and I'm spinning it around my head and it's going in a circle. Now, if the ball doesn't break off and fly and just go away, it'll be moving in a circle, and the force that's keeping it inwards, or keeping it going in a circle, is the tension force that's in the string. Now, the tension force is going to be the centripetal force. But you can see that the physical force, the force that we actually observe in nature, is not centripetal force, it's the tension force. And so the acceleration due to that force is going to be the acceleration due to the tension, and we call that the centripetal acceleration. So if the acceleration is towards the center, we can say that AN would be equal to R. Now what's theta dot? Well, theta dot is just omega, so let's write it as omega. Omega squared towards the center. But what's omega? Omega is V on R. So therefore I can say that my normal acceleration is going to be equal to R times V squared on R squared, which is V squared on R. And if you are studying physics in your senior years, then you will probably have come across this expression for centripetal acceleration. Okay, and the final thing that we can say or talk about is if we're moving with a uniform circular motion. So, if we're moving in uniform circular motion, what's the condition for that? Circular motion. The condition would be that the acceleration, theta double dot, is equal to 0. That means that the speed or the velocity at which, the speed in which we're moving around the particle, around the circle, is constant. So there's no acceleration. So if that's the case, well, what does that mean? Let's look back at our accelerations. Well, this is unaffected. The normal direction force, acceleration, is unaffected by the theta double dot, but the tangential acceleration is affected, and so the tangential acceleration will be 0. So therefore I can say that the tangential will be equal to 0, and so therefore the acceleration will be equal to V squared on R, or R omega squared. And this is only in terms of a uniform circular motion.